Let's look at a proof for the power rule of derivatives using the limit definition. Now, before we do that, I just want to note that if you're looking at something like x plus a squared, and you were to expand that out, that would be x squared plus 2ax plus a squared, where you kind of have the powers of the x's going down, and you have the powers of the a's going up. If you were to do this to the third power, you would have x cubed, x squared, x, and no x's at all. And as the x's are going down, the a's are going up. A squared, a cubed. And the numbers that go in front here are 3 and 3. If I were to do x plus a to the fourth, I'm really just trying to understand how powers work here. I'd have x to the fourth plus 4x cubed, picking up an a, plus 6x squared a squared, plus 4x a cubed, plus a to the fourth. If you're familiar with Pascal's triangle, the coefficients for these things are coming from corresponding rows. So for example, 1, 2, 1 for the first one, 1, 3, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And more generally, if I'm looking at x plus a to some nth power, it's always going to start out with x to the highest power. It's going to end with a to the highest power. And interestingly enough, check this out. 2, 3, 4. So whatever number the power is, that's going to be the second coefficient and the second to last coefficient. It's looking at sort of those outside pieces of the triangle. So I'm going to have some n times x to the n minus 1 times a, plus a whole lot of stuff in the center. And on the other side, I'm going to have n a to the n minus 1 and a single x. Okay, thanks for humoring me for that aside there, but I wanted to make sure that I understood how these exponentials were working when I was looking at something like x plus a or x plus h as it is. Because we want to look at the derivative of x to the n. And the limit definition says that if we're looking at the limit as h goes to 0 of f of x plus h, this function at x plus h, minus f of x all over h. Now let's expand that x plus h to the n. That's going to be x to the n times x to the n minus 1 times h, plus a lot of things that have h, higher powers of h, plus n times h to the n minus 1 times x, finally plus h to the n. So if I were to use this formula here, I could expand out that expression x plus h if I multiplied it. Now, I'm noticing that I've got xn minus xn. So those pieces are going to cancel. Limit as h goes to 0. And everything left here, n, x, n minus 1, h, lots of h stuff here, plus n, h, n minus 1 times x plus h to the n. And I'm going to divide all this by h. And what that's going to do for this first one is it's going to cancel out that h entirely. It's going to leave me with n, x to the n minus 1. This next thing is going to be something with an x n minus 1 times an h, all the way up to this last term is now going to be an h to the n minus 1. And the reason why I'm doing just kind of dots, dot, dots for all of those is all these remaining pieces have h, and h is going to 0. So that's a whole bunch of stuff times 0. So I've got limit h goes to 0, n times x to the n minus 1 plus all that stuff goes away. And the only piece that's left is this one piece that we were able to cancel that single h, that single term that was left over of n times x to the n minus 1. So to find the derivative of a power function using the limit definition, you do have to use the binomial theorem to sort of expand out that x plus h to the n. But when you do so, your x to the n terms cancel out. You get rid of one of the h's. Pretty much everything goes away except for the second term, this n times x to the n minus 1 piece hangs in there till the very end. The derivative of x to the n is n times x to the n minus 1. Let's check out more of these proofs together.